Good evening. Thrilled to be with you tonight. It's my third Astronomy on Tap, and I've been in the audience on the other two. And haven't Rachel and Jeff and their colleagues did a wonderful job, and haven't you all done a wonderful job getting this kind of turnout and enthusiasm for astronomy here in Austin. So I'm going to give you a little bit of information about McDonald Observatory and the giant Magellan Telescope. Let me just check things out here. How many of you have been out to McDonald Observatory before? Wow, that is a really impressive number. So hopefully we'll get the rest of you out there within the next year or so. This is an image of the Hobby-Eberle telescope in the foreground, our largest telescope at McDonald, and you can see our other two large telescopes, the Harlan-Smith telescope and the Otto Struve telescope in the background, and the beautiful Davis Mountains of West Texas. So, doing astronomy in Texas, what are the key advantages that McDonald brings to the worldwide astronomy scene? We have extremely dark skies in West Texas, and we really want to protect those dark skies. In the upper right, you can see, let me see, getting my laser working here. Well, not so working. But anyway, you can see where McDonald Observatory is, and those contours are where there's a lot of city lights and such, and get scattered up into the night sky. But you can see the area around McDonald is really dark. And we have very good legislative imperatives to do light pollution protection out there. So we got to keep the skies dark, because that's so important, both for the professional astronomy and for people who enjoy the skies just with their naked eye or with their own amateur telescope. It's a great resource. We have a varied set of telescopes at McDonald. Hobby-Eberle telescope, with its upgrade, it'll be a 10-meter telescope, and I'll tell you a little bit more about that. There's an image of the Hobby-Eberle telescope on the lower right, and you can see that the mirror is composed of segments. That's the new trend in telescope design, is not to try to make monolithic mirrors, but to make your collecting surface by ganging together smaller pieces of glass, smaller pieces that are more manageable. And with sensor and computer technology, you can do this. You couldn't do this in the days of the Palomar 200-inch or other historic telescopes, but that's a big piece of astronomy right now. Our other two telescopes are just a single monolithic mirror, the Harlan-Smith 2.7 meter and the Otto Struve 2.1 meter. We have a number of smaller telescopes, some of them used for professional astronomy, others associated with the visitor center, so you can go out there and look through them. Now, one of the things that really differentiates our telescopes at McDonald from others is really innovative instrumentation. You collect the light with the mirror, but it's how you slice and dice the light and detect it that really makes a difference. And we have a major instrument development program here, infrared spectrographs, light that's longer than the wavelengths you normally see with your eyes, multi-fiber spectrographs, very high resolution spectrographs. So it's a lot of the excitement in astronomy today is in the instrumentation. We're in the Northern Hemisphere, of course. And a lot of the new investment in astronomy has been occurring in the Southern Hemisphere because it was neglected. But there's really amazing things in the Northern Hemisphere that we need to see. Our nearest large neighbor galaxy, M31 or Andromeda, a lot of these deep fields are in the north, so we got to keep our Northern Hemisphere access. We have a strong group of astronomers who use the telescopes. You've met many of them here at Astronomy on Tap, professors at UT, researchers, students. But it's not only UT Austin that uses the telescopes. We have folks from Texas A&M, Rice, other UTs that use it, collaborators of Texas astronomers. So astronomers come from around the state and around the world to use the telescopes at McDonald. And finally, we test out a lot of new kinds of instrumentation to detect light in new ways at McDonald. The Hobby-Eberly telescope is one of the most exciting things we have going on at McDonald right now. So the Hobby-Eberly is being upgraded to have a much wider field. You'll see the field of 4 arc minutes there. That's the former size of the field we could see with the Hobby-Eberly in one exposure. The moon, of course, is around 30 arc minutes, and we're scaling it up to being a 22 arc minute field. So we'll have the same primary mirror, but all the equipment on the top of the telescope is being upgraded to bring a wider field into focus and allow us to survey the sky more effectively. So we're going to survey a big chunk of the sky spectroscopically with the Hobby-Eberly telescope. And in the next slide, I will show you what we're going to do with that. So this is the kind of science that'll be coming out of this, and I'm sure you'll be hearing about it at Astronomy on Tap and in the newspaper and in other ways. We're going to get the best measure of the expansion rate of the universe, and it's changed with time. So we're going to survey over 1 million galaxies, and we'll have the distances to those galaxies and the redshift, so we'll be able to see not only how the universe is expanding, but how that expansion has changed over time. So the accelerating expansion of the universe, we'll be able to probe it to the earliest epochs that are possible, and that'll allow us to understand whether this mysterious repulsive force in the universe, dark energy, has had the same kind of acceleration over the lifetime of the universe, or how it's changed. So we're the only experiment, and you've probably heard this in some of the other talks here at Astronomy on Tap, that's going to probe to the early lifetime of the universe, this expansion. Neutrinos, an elusive component of the universe, will get the best measure of the total mass of neutrinos. We'll find the oldest stars in the Milky Way. So this is a major topic, galactic archaeology, looking at the oldest stars to try to understand the properties of our galaxy early on and how it formed, what were the mergers or other processes that brought it together. We're going to study galaxies that form stars at such a prodigious rate early in the lifetime of the universe. Exoplanets are very hot. You'll hear about that in the next talk. And we're going to work very hard on finding and characterizing planets on nearby stars. And we're going to work very hard on the chemical composition of the oldest stars in the universe. Of course, the Big Bang, after the Big Bang, there was only hydrogen, helium, and a tiny bit of lithium and beryllium. All the other elements are cooked inside stars. So this is a big part of the Hobby-Eberly telescope's mission. McDonald, the rest of the telescopes on McDonald also have a bright future. We're putting innovative instrumentation on the older telescopes, so the telescopes are really reborn telescopes that date from the 60s or even 1939 can be very effective with new instrumentation on them. And on these older telescopes, there's not as many astronomers clamoring to use them, so we can support really long-term observing programs that go on for many years and create unique data sets, like monitoring exoplanets around nearby stars and such. And our educational mission is also really important. By having our own observatory, UT can train the next generation of instrumentation,alists, people who develop instrumentation on the telescopes, and the next generation of observational astronomers. In many programs, if you don't have your own telescope, people will just use data from archives. And our students and postdocs at McDonald can go out and use telescopes themselves. For all of you who raised your hands when I said, have you been to McDonald, engaging the public is a big part of what we do. And this is a picture of a star party underway. We do star parties, telescope tours. We do viewing through even the professional telescopes. So if you haven't been, go to our website, McDonaldObservatory.org, and there's lots of possibilities for planning your trip and enriching your trip with astronomy there. Now, one of the most exciting things underway in Texas astronomy is the giant Magellan Telescope. It's being built in Chile. It'll be the largest telescope in the world when it's completed in 2021. And UT is a 10% partner in the Giant Magellan Telescope. We probably have some Texas A&M people here as well. Texas A&M is also a partner. So we have 2 Texas institutions involved of the 11 partners. It's being built of 7 8.4 meter mirrors on a common mount. You can see them there. It'll yield amazing things in terms of light gathering with spatial resolution. So in terms of light gathering, it'll have 5 times the light gathering power of the largest telescope available today, the Keck telescope on Mauna Kea. It'll have, with adaptive optics, it'll have 10 times the resolution of the Hubble Space Telescope. So you've seen those beautiful Hubble Space Telescope pictures. Giant Magellan Telescope pictures will have 10 times the level of detail. It's at a great site in South America, and some of the top astronomy programs have come together to do this. We're really looking forward to UT having a big role in this. We're developing instrumentation for the Giant Magellan Telescope right here in Austin. And we're planning to develop a remote observing center so that we can get the data from this telescope in Chile right here in Austin. So there's an image of the 5 mirrors together, 380 square meters of glass. In case you were curious, it's a big step since pre-telescopic astronomy, 20 million times the aperture of the naked eye. And this is the sorts of things we hope to do with adaptive optics and the Giant Magellan Telescope. This is a star that most of the light has been canceled out of, and these are simulations of planets at different distances around that star. So that's half a Jupiter mass planet right there, a 1 Jupiter mass planet. So you can see we'll be imaging planets lower than the mass of Jupiter around nearby stars, which is tremendously exciting because kind of the holy grail is imaging a low mass planet and taking the spectra of its atmosphere and seeing what's happening in the atmosphere of that exoplanet. This gives you an idea of what this gain in resolution will do. So this is an image with a typical ground-based telescope without adaptive optics. So the resolution is controlled by the blurring of our atmosphere. Here's Hubble Space Telescope of the same field. So you can see, if you go back and forth, you can see only the bright stars in that, but a sea of faint stars starts to come out because Hubble does not have the blurring of the atmosphere. But from the ground, we can build huge telescopes. Your resolution increases in proportion to the diameter of the telescope. So in theory, the Giant Magellan Telescope can have 10 times the resolution of Hubble Space Telescope, going from 2.4 meters to 25 meters. But you have to fix the atmosphere, and that's what adaptive optics does. So this is the gain from Hubble to GMT. So I think you can see why the astronomy community is so tremendously excited about this. How do you make a 25-meter telescope? Well, fortunately, one of our partners is the University of Arizona, and the Stewart Observatory Mirror Lab there makes mirrors underneath the football stadium, and we are about to cast our 4th mirror. On Friday, we will be casting the 4th out of a total of 8 GMT mirrors. 7 will be in the telescope and 1 spare. So it's pretty simple. You take 20 tons of glass, you put it in a rotating oven, and you heat it to 1700 degrees Celsius. So in order to keep the mirrors lightweight, you put in a bunch of forms to sort of take up airspace in there. So those get blasted out after the mirror is cast. And here's the finished mirror. So it's huge, and it's a pretty routine process now. And we'll have 7 of those working together at GMT. So stay tuned for the casting on Friday in Tucson. This is the GMT site. So many of you have probably heard of Las Campanas Observatory and the Magellan telescopes. It's on that peak, and the GMT will be on this peak. It's one of the driest areas on the planet. It's come in first place in all of our site testing. There's infrastructure there. You can see there's roads, power and water, communications, so we don't have to put all that in. And the Carnegie Institution owns this site, a large area around it, and has protected it from light pollution and from mining. So let me show you a little movie of what the GMT will look like. There it is, all done, and there's the other telescopes down there. GMT sits alone on this peak. It's at about 8,200 feet, which is a really good elevation for astronomy, but it doesn't get very negatively affected by the winter weather down there. If you get higher, you have problems with the winter storms, and you don't have to worry about supplemental oxygen at 8,200 feet. You can see it's right at the crest of the mountain, so the wind that hits the telescope won't have gone over any near disturbances most of the time. And you can see our seven mirrors, and the secondary mirrors held up by a very compact arrangement that doesn't block much of the light. Here's the dome opening, kind of an unconventional dome. We don't have anything like it at McDonald. These are the mirror covers, which will open next to reveal what's going to collect the universe's secrets. These are where the lasers launch for laser guide star adaptive optics. And it's an altitude azimuth telescope, as most large ones are, so it doesn't have axes aligned with the equator and the pole, but it has altitude and azimuth. And we're just going to fly into the instrument area, and then I will stop the movie. But this is where the light comes to a focus, and the instruments are, and this instrument right here will be developed in Texas. It's called GMT NIRS. It's a high-resolution near-infrared spectrograph. Oops. So this is just to give you an idea of the size of GMT. I think most of you are probably familiar with the UT tower. This is GMT in scale with the UT tower. So you can see this is huge. Don't try to build this in your garage. And you know, it's almost as tall and much wider. But when you think about the accuracy that you need on these mirrors, you know, we have to hold the surface on those mirrors and then the distance between the primary and the secondary to a 20th of the wavelength of light. So that's a 60th of a micron. So it's really an incredible engineering challenge in addition to being an astronomical challenge. Here's the GMT Partners. You can see we have 2 Texas institutions, and the total project is going to be about $1 billion. $500 million have been put in so far. UT Austin has put in $50 million. So we're 10% partners so far, and we're trying to maintain a 10% share so that we have 10% of the observing time and 10% of the intellectual share. So we're working to raise a second $50 million via philanthropy. And this is a picture of laser guide star adaptive optics with GMT. And I'm gonna close with this image, but Jeff and Rachel asked me to say a little bit about what happens behind the scenes at an observatory. You know, what does a director do? And what do all the people who aren't, you know, observing with the telescope and getting data do? Well, laser guide star adaptive optics is an interesting fable because you have to develop the lasers, they have to work at the sodium wavelength, so that's a whole challenge in and of itself. But once you have the lasers and you know the objects you want to point them at, you know, the interesting objects in astronomy, you have to get permission from a lot of people. So you have to make sure you don't illuminate any planes with the lasers, first of all. So GMT will shoot these lasers. The observatory that pioneered this the most strongly is Keck Observatory in Hawaii, and I was director there for about a decade. And we had to make sure we didn't hit any planes flying around Hawaii with these things. We had to get permission from the Federal Aviation Administration. They thought we would blind pilots. So the first thing we did is we had University of Hawaii Hilo students stand outside with night vision goggles and a hula hoop. And if they saw a plane, they put a hula hoop with the plane in the center of the hula hoop, and if the edge of the hula hoop came near the beam, they had a dead man switch, and they'd let go of it, and the laser would stop. And we got that certified by the Federal Aviation Administration. We decided we were freezing too many people that way. So we then developed a system that talked to the transponders on the plane so that it wouldn't hit the plane. So that was good. But the planes weren't enough. We then had approved to the U.S. Space Command that we weren't going to hit any U.S. spy satellites, or even worse, Russian or Chinese or North Korean satellites. So every night, an observatory that's going to do this has to send all of its targets to Space Command. They will then cross-correlate all the targets with where all the satellites are orbiting. And they won't tell you where the satellites are, but they'll tell you when you can't observe your target, so you don't illuminate a satellite. And if you don't follow all these procedures, like if all of a sudden in the middle of the night you discover some cool new thing and you want to go to, you got to call Space Command, because they'll shut you down if you don't follow these rules. And our host Rachel has even been shut down for a night, but through no fault of her own, I might add, but by Space Command. So it can be kind of heartbreaking. So there's lots of people behind the scenes besides the astronomers, the software people, the engineers, the technicians that make all this magic work and allow us astronomers to do our job. And they're very committed. And thank you for coming tonight.
Okay. We have time for a few questions with Director Taft. And I'm very thankful that by the time I became an observational astronomer, they did not put us outside of the dead man switch. that was a scary prospect. Let's see. Questions. Oh, straight in the middle here. There we go. Thank you.
How are the mirrors moved from Arizona to the Davis Mountains without breaking up?
Yeah, that's a great question. And then we also have to move them to Chile. So we just recently moved this wide field corrector that's going to be on the Hobby-Eberly Telescope from the University of Arizona Optical Sciences to the Davis Mountains. We had two UT police cars, one that was in the front and one that was in the back. So thanks to the UT police. And we had it on a flatbed with a specially engineered set of springs underneath it to take out all the bumps. We had done previous test runs on that route with little seismometers attached to those springs and a mast that was the dummy size. We drove the road beforehand looking for potholes. So it's incredible. And now we've got to get these mirrors that are 8.4 meters in diameter from the University of Arizona down to Chile. So the plan is, the plan was, I'm not sure what the plan is now, but the original plan was we would truck them down to a port in Texas. I'm pretty sure Corpus Christi. And then they would go by ship through the Panama Canal down to Coquimbo, Chile. They'd be offloaded, and then they'd be driven up the Pan American Highway. It would have to be closed to allow them to get there because it's not wide enough. We had Chancellor McRaven visited the observatory this summer, and he suggested we should just put them in a C-5A and fly them down there, because he used to be with the military, and he said he'd put in a good word for us. So I will update you as to whether they go by ship or C-5A.
I like that. Cargo plane. Right here.
Yeah, that's a great question, because... sorry. The question is, how do you keep the mirrors free of dust? Most astronomy sites are extremely dry, right? So you have a lot of dust, and they tend to be kind of windy as well. Mauna Kea, West Texas, so we get a lot of dust on our mirrors. We do something about once a week that's called CO2 snowing. So we take liquid carbon dioxide, we shoot it out into the atmosphere. It forms a slurry when it hits the mirror, kind of like snow. And it goes down the mirror, and CO2 doesn't react with the aluminum on the mirror. And it kind of entrains all the dust with it. And we do that about once a week. It cleans it off. You have to re-illuminize the mirrors about once a year or once every 2 years to keep up their maximum reflectivity. So we have to pull them out of that array of mirrors, strip the aluminum off, put them in a vacuum chamber, and deposit a new really thin layer of aluminum on them.
All right, one more question for Director Taft, straight back here.
Yeah, our observatories tend to be in seismically and volcanic interesting areas. Not so much McDonald. McDonald has been judged one of the most stable places on Earth, I'm told. And this is because we do lunar laser ranging from there. And the USGS and people like that who need a reference frame say McDonald is very stable. But places like the observatories in Chile, and particularly the observatories in Hawaii, are not so stable. So we have two precautions against volcanic and seismic activity. One of them is all the telescopes are built to a very high earthquake tolerance so that they have extra heft in all the mechanicals so they can withstand an earthquake. And when I was at Keck, we had a magnitude 6.5 earthquake, and the telescope survived fine. And then all the software can take new 0 points for the pointing each night. So if there's an ever so slight movement of, say, Hawaii Island, compared to the whole astronomical reference frame, it gets taken out at the beginning of the night each night. And every time there's a major earthquake, we have at Keck we had a sequence of events we went through to make sure nothing had moved enough that things would hit each other. But it's a great question.
Yeah, I'll add that the California observatories have similar redundancy. All right, let's thank Director Taft one more time. He'll be around for a while to take questions.